Hey, all ready to go. It's really great to be back here. I've participated with Asgard for many years. I was here for the first one, and in 2011. And Eric always puts on a fantastic program. So just thanks to Eric again. So Eric asked me to speak a bit about some applications of gas discharges in space and near space. And when I started doing my slides, I realized this is just a massive subject. So I'm going to narrow it down. I'm going to narrow it down to one application. And it's application, there we go. It's the application that I worked on for my PhD. So last century. I recently got a reference on ResearchGate, and the citation said early work in this area, and referenced my thing. So I'm now early work, not last century. So it makes me feel old. So this is the application I was working on. This is a Kaufmann type ion thruster. And the bit I was looking at specifically was the hollow cathode, which is there. Now this has many different discharge environments in it. So it covers a whole range of pressures and conditions. So on the right here we have near vacuum in space. On the left we've got maybe 100 pascals. So much lower than atmospheric. Atmospheric is like 100,000, so it's 1,000 times lower than atmospheric pressure, even in the high pressure part of the ion thruster. So the reason we want to use an ion thruster is we get very high speeds of the propellant, which means for big mass transfers in space, you don't have to carry as much propellant. But the force that this produces is really small. It's about the force of a piece of paper sitting on your hand, and you've got this massive kit, so many kilograms. So it's no use either in atmosphere, because the pressure is too high, or to get things off the ground. But when you're in space, just a little force over a long period of time, if you've got a very high propellant rate, can give you big changes in speed over days or weeks, rather than the big rockets that you need to get off the ground. Okay, so now onto the discharge physics. So we have the cathode here. The anode is in this discharge chamber, and there's a discharge between the cathode and the anode. Creates this plasma in here, and then we've got grids. The inner one is held at a very high potential. So all of this is raised to a very high potential. So you ionize your gas at a high potential, and then the outside grid is the same as spacecraft neutral. So it accelerates ions out through the grids and gives you your thrust. To get this plasma, we need to initiate a discharge between the cathode and the anode. Now, this is where we look at the discharge physics of gases. And this is applicable to a whole range of different phenomena, and possibly some Asgard missions. So before there's a discharge, we have, this is the voltage, and this is current over several orders of magnitude. Down in this section, if you've got a gas, you will have ionization events from cosmic rays or radiation all the time. So there's charged particles there already. Even if you try and get a vacuum, even our best vacuums, there's going to be some material, there's going to be cosmic rays going through. The idea of a perfect vacuum, when you look at the physics of it, isn't really a thing. There's always going to be something there. So you start with some ionization event. The first little blip from the origin up to A is just you accelerate those charges and they end up at the electrodes. So you've got ionization, the ion will go towards the cathode, the electron will go towards the anode, and you can detect that current if you've got sensitive enough electronics. So you have an ionization chamber, you can detect that current. Then you have an increase in voltage. It starts to cause what's called a Townsend avalanche. Okay, so here's my original ionization. Now instead of just drifting to the anode, the electrons go up here and the ions go down here. Now the electron is accelerating. It accelerates, it gains enough energy in the electric field, and it hits another neutral atom and creates another electron. So this is the original electron, keeps on going. You get another electron. This ion will then drift back to the cathode. So it's a bit like the chain reaction you get in a nuclear bomb. So one reaction leads to another reaction, leads to another reaction, you get an avalanche. Okay? So the first two steps of starting a discharge, you've got ionization, and then you've got avalanche. Okay, so this is the Townsend region, and this is the region a Geiger tube would work in. So you set up your voltage, so you're having extra ionization, and you'll be able to detect a larger current. Geiger, because it's multiplying the charge, you can't really identify what type of radiation so well as ionization chambers, but you get a much clearer click that's easier to detect. Now, I mentioned that ions heading back towards the cathode. And there's a third stage that happens in gas discharges. We go back, we're going up here now, away from Geiger tubes, up into a corona discharge, and then you get to this point, all across this region, we're having ions hitting the cathode. Now, if they just hit the cathode with low energy, they'll just be neutralized. So they're transferring charge there. But as you increase the energy of them hitting, they will start to release extra electrons. Okay, so now if you have secondary electrons at the cathode, can you see what's going to happen? So we get electrons, secondary electrons generated here that are going to be accelerated to the anode, causing extra ionized events, causing more ions to go back to the cathode. You get a feedback loop, okay? And that causes breakdown. Okay, so now we have it's not just the avalanche discharge of the Townsend discharge, we have the normal glow discharge on the cathode, and the gas becomes conducting. We have a plasma. Okay, so for the discharge, to explain this, you get the three processes: ionization, then the avalanche, and then feedback loop. Okay, so this is feedback loop from those ionization, the secondary electrons, and then as we increase the current more, the area of the cathode that's active gets larger and larger and larger until the cathode's fully covered, and then you're increasing the energy of those ions hitting the cathode, you increase the heating, and eventually you get thermionic effects dominating, and you get a second transition from the glow to what's called an arc discharge, which is thermionic emission dominates. Okay, so that's the general shape. In the experimental setup that I did, we have high pressure gas coming in here, discharge initiated between what's called the keeper electrode that just keeps the discharge going, so it doesn't quench as easily. And then we just had an anode. We had no magnetic fields to confine, because no grids. We were just looking at the internal. Basically, I was looking at the cathode and the starting of this. A couple of additions to this cathode, so there's slight differences between a normal discharge tube and this. So we've got very high pressure gradients, and we've got it heated, so it's not a cold cathode. And we've got an emitting insert with low work function, so we make it as easy as possible to get those secondary electrons. And it's more complex geometry, and there's gas flow speeds, but the main law for breakdown applies to this. You can apply the Paschen's law breakdown to pretty much every gas phenomena in some ways. It'll have some applicability. Okay, so I'm going to show how those three processes, or with the breakdown, so ionization, avalanche, and then the feedback, the breakdown, can be modeled. And the actual voltage that we got to break down, so with the heating, so we've got, these are volts, these aren't kilovolts, so with a heated insert, we were getting, with a heated tip temperature of 1,000 degrees, you've got 14 volts to initiate a discharge. Okay, so those secondary electrons were really easy to generate in our system. And there's a constant called the Townsend's constant, second constant, that gives you a number of secondary electrons per ion, and that's in here. So if this becomes large, then the voltage that you work out becomes very small. So this is increasing Townsend's second coefficient, the number of electrons released per ion, and you get a really low discharge voltage. Okay, lastly, the voltage, breakdown voltage in relation to pressure times distance. Now, this bit of the graph seems intuitive enough. If we go back to here, if I, so thinking about the avalanche, the amount of energy an electron has before it loses it is the distance it moves before it has a collision. Okay, and it needs to gain enough energy to ionize something. If it hits something before it gains enough energy, it won't ionize something. So it needs to accelerate to the ionization energy and then hit something. Okay, so if you have too much gas in the way, the electrons accelerate a wee bit, and then they get stopped, so you need a higher voltage, or a lower pressure to give them longer to accelerate. Okay, so if you, that pressure times the distance between the electrons, or the electrodes, gives you an idea of how many mean free paths you have. When you divide up the voltage by the mean free paths, you'll get how many ionization. Good question?
Yeah, and your experiment setup, you use xenon gas, I believe?
Xenon gas, yes.
Is there a particular reason? Because I think like argon would be much easier because it's a smaller atom.
Yes, that's right. So if you're talking about specific impulse, the lowest mass is what you want. So hydrogen theoretically would be give you the highest specific impulse. So if you accelerate it to a kilovolt, you're going to have a much higher speed for hydrogen than you are for xenon. Xenon is heavy. Two reasons for xenon. One is it's very easy to ionize, but the fact that it is heavy means you get bigger mass for transfer. So it's a compromise between the amount of force and the specific impulse. So in a sense, argon would be too good for some applications. Yeah. So you want to be able to do things a little bit more quickly than you would with argon, but still have higher specific impulse than you know, a chemical rocket or something else. Okay. So, good question. Yes. This side of the curve is when you have too many gas atoms in the way and you lose energy. As you go down to a low enough pressure or a close enough distance, there's just not enough gas in there. At low pressures, too few collisions, so you have to increase the voltage to increase the probability of an ionization event. Okay, so at low pressures, like in space, you need high voltages, and at high pressures, where there's lots of collisions, you need high voltages, but in near space, you need low voltages, okay? Which is the thing that you need to design for when you're potentially doing a high voltage experiment in space. I don't know how long I've spoken for. Maybe I should take some questions. That's some of my results with the passion curve fit. So down to 12 volts, that's the tip temperature. So it's a heated cathode insert, low work function. And these are millimeters between, so it's about 3 millimeters between the keeper electrode and the cathode. And I can change that speed, and I can see that passion curve. And that's the cathode tip. Center orifice is about 1 millimeter, to give you a sense of scale. Okay, any questions? Yes?
Can we see it in action?
See it in action?
Yeah.
On YouTube or something?
Yeah, like anywhere.
I could Google on YouTube. Or maybe I'll post a video later. I'll take more questions and
Alright.
you can. But yes, definitely there's. Yes.
How do you cool down the setup? Because
it's just radiative. So in space it will radiate. On our cathode, we want to keep it as hot as possible, with minimal transfer of heat to the rest of the spacecraft. The cathode being hot is the main thing that we want for the discharge. So it's got a heater inside the cathode to get to the initial temperature, and then around that it's got lots of layers of molybdenum foil, so that to minimize radiation. So, yeah. Any other questions? Whoops, that's.
I have one, Stephen. If we're going to have electronics on an Asgard gondola that uses voltages of several hundred to possibly even over 1,000 volts, I mean, you need like what, 400, 500 volts on a Geiger counter, and we send up photomultipliers that take 1,000 volts to operate. In your experience, is a straight conformal coating enough to prevent any discharge phenomena, or do we need to cast it in epoxy, or?
Yeah, so key thing is breakdown of plastics on Earth is going to be the same as in space. Very, very similar. So you can get high voltage heat shrink, hot glue, some high density polyethylenes get a very good breakdown over a few thousand volts. You coat everything in electrical tape and hot glue. Hopefully we've got enough hot glue on our Geiger tube this year, but this is the way to go. Our previous experiment, we had a dust collection experiment where we had electrostatic plates, and we worked out we could have them a few centimeters apart without causing breakdown. So that would, if there's any charged dust, it would be attracted to one of the plates. And then everything else that was closer than that, we coated in insulating. So at ground level, breakdown for air is about 30 kilovolts per centimeter. So if you multiply that up, so if we've got 100th of the pressure, so then we're kind of scaling that by 100 times. So 30 kilovolts a centimeter, that's 3 kilovolts per millimeter. 3 kilovolts over a centimeter would break down in near space. So if you've got things that are closer of the order of that, if you've got 1,000 volts over the order of less than a centimeter, then you will get breakdown. Okay, I don't know how long I took. Do you want any more questions?
I don't know. Are there any more questions? Then thank you, Dr. Patterson. No.
Thank you very much.
Okay, so for those teams who consider flying high voltage equipment, there's a number of things to bear in mind. One of them obviously being that if you're going to use high voltage, you need to be careful.